Hello and welcome to another IOP Waves Domain video. This video is all about the Ripple tank. In the first half, I'll be showing you how to build one and take measurements from it.
And in the second part, I'm going to show you how you can use some online simulations to really develop your students' understanding of waves.
So as you can see, we're really hoping this video makes some waves. Let's just get started, shall we, and get to our lab. Okay, so here's my Ripple tank. It's worth saying that there are many different types of Ripple tanks out there, some very high tech, some very low tech. This is a low tech one. This is one of the most basic and ubiquitous tanks you'll find out there. You've got just a few components: light source, legs that can be adjusted to get the tank level, springs to suspend the motor that will oscillate, a way to speed up and slow down the motor, and then a tank to put our water in. What I'll do now is I'll put this together so you can see how we do that. Okay, so that's the tank built. Now it's time to add the water. Now when you add the water, less is more. Too much and you start to get refraction effects, and the lines you get, the ripples you get won't be as sharp. So about 5 millimeters from the base will be plenty. So I'll be using a ruler when I add the water to see how deep it is. I'm making sure the water's not pooling to one side. I'll use the adjusters on the legs to keep it flat. And then when I've got all that sorted, I'll make sure that this bar is just kissing the surface of the water by adjusting the height either side here. Okay, so after all that, it's ready to use and it's working pretty well. One thing I have done is I've turned the lights out in the room and I've put some white paper down here so we can see the projections a bit easier. So now we can start taking measurements. Now the whole point of this is to take measurements of wavelength and frequency to then calculate the wave speed of these ripples. And we might want to vary the frequency of the ripples to see how that affects the wave speed. So let's start by doing the wavelength. Right, so measuring the wavelengths is actually the easiest part of doing this. Now at the minute we can't do that because the waves are all moving. So we need a way to freeze them. That's where our camera comes into play. Taking a picture of this will freeze the waves in place. Having a ruler in the shot is crucial if we're going to then measure the wavelength. So I'll do that now. And then that's what I get. Let's now take a closer look and calculate that wavelength. Okay then, so here's a better look at my picture. So the question is, between which 2 points do we measure one wavelength? So to imagine that, I want you to imagine the light coming down from above and then being focused by the ripples. You can see on the peaks, the light's being focused into our bright lines. So at each bright line, that is a peak. So brilliant, got the answer. You can simply measure between a bright line and another bright line, and that is one wavelength. Now, it's a bit hard to determine where is the middle of that bright line. It's actually easier to say, well, let's take this like leading edge here. I can see that easily. So there we go. It's still one wavelength, just a bit easier to discern. So let's go through this and pick out all my wavelengths. So I've got one start here, finishing there, another one there, another one there, another one there, and then finally there. So I've got 1, 2, 3, 4, 5, 6, 7 wavelengths. And you'll notice they're all slightly different. So in order to overcome this and get more accurate results, let's take an average over those 7. So let's see, where's the start? 13.7 centimeters. And then over here it finishes at 32 bang on centimeters. Okay, so what we can say is 7 wavelengths is equal to that gap. That gap being equal to 32.0 minus 13.7. So 7 wavelengths equals 18.3 centimeters. We want one wavelength. So let's divide both sides by 7, and we get 1 wavelength is equal to, divide that by 7, 2.6 centimeters. So there's our answer. The average wavelength in this scenario is 2.6 centimeters. Okay, so now we want to measure the frequency. If you've got a high-tech tank, you might have a frequency readout on the side of yours somewhere telling you the frequency. So in that case, you're done. If yours is more basic like mine, we're going to have to figure it out. To do that, we're going to count how many times that motor oscillates in 1 second. Now, that's getting a bit fast for my eyes. So what we'll do is this. On most phones these days, they have a slow motion feature. So I'm going to use my phone to record that in slow motion. I'll watch it back, and I'll count how many times that spins around in 1 second. Now, knowing how long 1 second is a bit tricky, but not if you've got in the background a stopwatch. So when you record this motor spinning around, make sure in the background there's a stopwatch so you can scrub the video for exactly 1 second and count those oscillations. So I'll do that now, and I'll show you the video next. So here's my video of my motor spinning. You'll notice the stopwatch hasn't started at 0. That doesn't matter. All that matters is we have at least 1 second to look at. I'm going to scrub my video, and I'm going to find 1 whole second. So let's go and find 31 seconds. Right, it's often very hard to get exactly the time you want, but 31.01 is good enough. Just going to make a note of where the motor is in its spin. So it's pointing to 9 o'clock, let's say. So that is where it's going to start. And now I need to just count forward, count for 1 whole second, and see how many times this motor spins in that 1 second. So here I go. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, almost there, 14, right, so 14.5. So if that motor's spinning 14.5 times in 1 second, that means the frequency of our ripples is 14.5 hertz. Now we can bring that together with the wavelength calculation to calculate the wave speed. Let's do that now. Right, so we've reached the final stage. We've taken measurements of frequency and wavelength. Now we can use the wave equation to calculate the wave speed. Let's start by writing down what we know. We measured the frequency to be 14.5 hertz and the wavelength to be 2.6 centimeters. And before we carry on, let's make sure that our values are in SI units. For frequency, that should be hertz. Now ours is already in hertz, that's great, it's good to go. Wavelength needs to be in meters. Now we've got centimeters, that's the problem. We need to convert that. Now knowing that to get from centimeters into meters, we have to divide by 100. If we do that to our value, then we'll get our answer in meters. So 0.026 meters. And this is the value we're going to use in our wave equation. So let's put the numbers in. So our wave speed equals frequency 14.5 times by wavelength 0.026. Gives us a wave speed of 0.377 meters per second. Now at this point we want to round. Now how far do we round is a good question. We look at our values that we use to calculate the answer, and we look for the one with the least number of sig figs. In this case it's the 0.026. This one is the 2 significant figures. So we'll round our answer to the same. So we're going to round this to 2 significant figures and get 0.38 meters per second. So there you have it. The speed of our ripples was 0.38 meters per second. So there you go. That's all there is to it. Now in the lesson, what I do is demonstrate this method first, then I change the frequency and get students to come up in their pairs, take pictures, take videos, and then do the calculations themselves at their desk. The really nice thing is that regardless of the frequency, you'll get the same wave speed. It's a great way to check if you've done it right or not. If you can't do this method in your school for whatever reason, I've attached some supporting documents to help you. I've taken some more pictures and some more videos of different frequencies, so you can have a go at those instead.
There are also some excellent simulations online that you can use, which can really help your students with their understanding of waves. The one I'm going to show you today is the Wave Intro simulation, which is available on the PhET website. These are a comprehensive set of interactive animations produced by the University of Colorado. These are freely available and well worth having a look at. When you open the simulation, you can choose water, sound or light. I'm going to use water, but the others are great to explore as well. You'll notice it's set up as a tap which drips into a reservoir of water. This is a great way to bring some science capital into your teaching. It's more likely your students are familiar with a dripping tap than they are with a ripple tank or a wave generator. So this is something they can relate to from their everyday experience. You start the tap dripping by clicking the green button. You can then choose a single drip, which gives you a single wave pulse, or you can change to a regular drip, which gives you a continuous wave. You can also adjust the amplitude and the frequency. Students are probably most familiar with seeing water waves in a ripple format from above, either from a dripping tap or ripples on a pond. By changing to the side view, however, they can actually see what's happening in the water. In the side view, we can see the drip sinking into the water and creating a trough. We can mark the position of this trough on the screen and of other troughs. If we then change to the top view, we can see that those troughs align with the darker rings that we can see across the reservoir. We can also do this with crests. If we go back to the side view, we can identify areas of maximum displacement and then look at it in the top view. We can see that they align with the lighter rings. This is a great way to help your students link crests to wavefronts, and they'll need to understand this later when they're using the ripple tank to measure wave speed. To build their understanding of wavefronts, I can use this tool here, which is a water level probe. If I put one of the probes into the reservoir, I can see the water level, which is measured on the y-axis, rising up and down, with time on the x-axis, as we see the wave rippling across the reservoir. I also have tools to make measurements of length and time. This offers a huge amount of versatility for developing a thorough understanding of waves. Because I can control the frequency and measure the wavelength, I can get students to investigate the relationship between the two by simply asking them to measure the wavelength at a low frequency and then again at a high frequency. This is made much easier in side view, and also because I can pause the animation. So, if they move the frequency to a low value, wait for the simulation to respond, and then press pause. They can use the tape measure to measure the wavelength. If they want to improve the accuracy of the measurement, they can use this graphing tool here. Once they've got this measurement, I can simply ask them to repeat it again, but moving the frequency to a higher value. Again, wait for the simulation to respond, press pause, and then measure the wavelength again. Immediately, they can see that by increasing the frequency, the wavelength has decreased. And again, if they want to improve the accuracy, they can do this using the graphing feature. You may have noticed that there's no values for frequency, but this is a great reason to introduce how to measure frequency to your class. The easiest way to do this is by using the timer and timing how long it takes for a certain number of drips. So, if I wanted to measure for 5 drips, I'd start the timer and start counting until I'd had 5 drips when I'd stop the timer. Let's give it a go. 0, 1, 2, 3, 4, 5. So I had 5 drips, which took 8.22 seconds. To find the frequency, we need to remember that frequency is equal to the number of oscillations divided by the time taken. So in this example, the frequency is equal to the number of oscillations, which is the number of drips, which is 5, divided by the time taken, which was 8.22 seconds. So for this example, the frequency was 0.6 Hertz. Once students have measured the frequency and the wavelength, they can calculate the wave's speed, and they can investigate the relationship between frequency, wavelength, and wave speed. Once they do this, they might find the idea that the wave speed is constant regardless of the frequency challenging to understand. But because the medium the waves is travelling in and the depth is constant, the speed won't change, but the wavelength does. We can show them this. If they watch the far side of the screen over here, and they change the frequency from a high value to a low value, they can see the wavelength increase, but they'll notice that the speed remains constant. We can look at this in the wave speed equation as well, where speed equals frequency times by the wavelength. If we increase the frequency, and we know that the speed is constant, then the wavelength must get smaller. Conversely, if we decrease the frequency, then the wavelength must increase for the wave speed to remain the same. Hopefully, this has given you some ways you can support your students' understanding of waves and really make the most of exploring waves in a ripple tank in your lesson. Thank you.
We really hope you found this video useful. If you have any more questions, please look out for our accompanying workshops at talkphysics/events.
And don't forget to check out our other domains videos available at spark.iop.org.